Hi, George Diamond here, and welcome to our next video in our flipped video classroom series. Now today's video is going to be, we'll be introducing and talking about implicit differentiation. Now let me mention the purpose for my videos. I teach AP Calculus, and we're in the process of flipping a couple of units in AP Calculus. Now we're not going to be able to flip all of our units probably, but certain units we're going to flip. That is, my students are going to be watching video number 1, the introduction to implicit differentiation. In video number 2, right, they're going to look at some examples of implicit differentiation. And when they come to my class the next day, okay, we're going to work on homework together. So they're going to work on homework in groups. They'll have me there to ask me questions. They can kind of use me as a resource. And hopefully, so far we've had some pretty good results using the flipped classroom model. So it's been fairly successful for us so far. So let's go and get started with our video today. Now this is over in our textbook. This is section 2.5, implicit differentiation, video number 1. Now remember, there won't be a lot of examples today. That'll be in the next video, video number 2. So let's get started. Okay, a couple of essential questions first to begin. What is the difference between implicit and explicit differentiation? So the first thing we'll look at is what's the difference between implicit and explicit differentiation. Number 2, how do you use implicit differentiation to find the derivative of a function? So how do we actually find the derivative of a function that's in implicit form as opposed to explicit form? All right, so let's get started. Let's take a look at some functions here that are first of all, let's go ahead and describe the difference between implicit and explicit functions. So what do you mean by implicit and explicit? Now first, if a function is in explicit form, basically it's been solved for y. Okay, this is where the variable y is written as a function of x. So it's been solved for y. Okay, now if a function is in implicit form, that is the function has been implied, all right, so the function is in implicit form. Okay, this is where a function is only implied by an equation. So we've got an equation, but it hasn't been solved for y yet. Now we can still take the derivative of it though. All right, so even though it's not been solved for y, we can still take the derivative. Right? And in certain cases where some functions, it's very difficult to solve the equation for y in terms of x. But it's very easy to get the derivative the way it sits. Without doing anything to it, we can just take the derivative. So let's look at some functions that are in implicit form and the same function in explicit form. Now remember, explicit form means the function has been solved for y. Right, so it's been solved for y. So let's start off with a little parabola. Here's our first one. Okay, 3x squared minus y equals 5. Now this is implicit form. Now we can take the derivative of this function the way it is. Right, so without doing anything else to it, rearranging it or anything, we can take the derivative. Now, the same function solved for y is this right here. So y equals 3x squared minus 5. We're just basically moving the 3x squared over, changing the signs. That's the same function solved for y. Now, to take the derivative of this function is easy. So just like we normally have, use the power rule. So very quickly, we could get the derivative of one that's been solved for y. Next, x times y equals 1. This function is in implicit form. Now, the same function that's been solved for y in explicit form is y equals 1 over x. Now, once again, very quickly, we get the negative exponent, but we can quickly take the derivative of that. Another example. Looking at our third example here, this is x squared plus y squared equals 4. Now, this would be a circle. And solving, now this would be in implicit form, right? So it has not been solved for y yet. Right? Now you take the circle and you solve it for y, and we get this equation here. Y equals plus or minus the square root of 4 minus x squared. So if you're looking for the derivative, it may be easier to find the derivative of this particular equation in implicit form. Right? So x squared plus y squared equals 4, we can get the derivative very quickly. If you're going to get this derivative, you'd have to use the chain rule. Right? So it's probably easier to take the derivative in implicit form. Okay, let's get one more example. Now look at this equation here. Now we got x squared minus 2y cubed plus 4y equals 2. Now, what if we solve this equation for y? So what would we get? Now, who knows? I don't know. This equation here would be particularly difficult to solve for y. It'd be very difficult. I'm sure it can be done. I didn't do it. I'm sure it can be done, but it would take a while for me to figure out how to solve this one for y. But, you know, if I have to get the derivative of this function, I can get the derivative very quickly. Right? We don't have to solve this for y. Solving for y would be the really hard part if we had to, but if all we need is the derivative, so we can get the slope of our tangent line or something, we want to take the derivative the way it is. Okay, you don't want to spend 30 minutes solving it for y and then take the derivative when we get the derivative in 1 minute. All right? Okay, so a little bit about derivatives of variables. All right, so a little bit about derivative of variables. Now, start taking the derivative of x with respect to x. Now, we know how to do this. We've been in this for a while. Now, the derivative of x with respect to x is 1. All right, so that's easy. Now, one thing about this derivative, the variables agree. So you're taking the derivative of an x expression with respect to x, the variables agree. All right, so you take the derivative the traditional way, that just gives you 1. Now, if you take the derivative of y with respect to x, now remember now the derivative of x is 1, so the derivative of y with respect to x is, now once again, as you look at this here, the variables do not agree, right? So if they don't agree, and you're taking the derivative of a y factor with respect to x, is 1 times dy over dx. So the derivative of y with respect to x is actually dy over dx, or dy over dx times 1. Now, let's look at a couple more examples here where the variables agree and where they don't agree. So maybe this will kind of help a little bit. So let's take a look at a couple of these. Differentiating with respect to x. Let's try x cubed first. So the derivative of x cubed. All right, now we know how to do this. Once again, the variables agree. Okay, we're using the power rule. You bring the 3 down front, becomes a factor. Subtract 1 from your exponent is 3x squared. Easy. All right, so easy. What if we had the derivative of y cubed with respect to x? Now this time the variables do not agree. Now remember now the derivative of x cubed is 3x squared. So the derivative of y cubed, you take the derivative the same way you take the derivative of x cubed, but we have to leave dy dx as a factor. Now let me point this out. The reason we leave dy dx as a factor is because we're actually using the chain rule. So with the chain rule, think of y cubed as the exponent as the outside part, and y is the inside part. So you take the derivative of the outside, which gives you 3 with an exponent of 2. You bring the y over, times the derivative of y with respect to x, which is dy over dx. Now, by using the chain rule, basically what happens is you take the derivative of a y factor just like you would an x factor, but you have to multiply that times dy over dx. So you get that extra factor in there, an extra factor. So it's 3x squared times dy over dx. So if the derivative of x cubed is 3x squared, then the derivative of y cubed is 3y squared times dy over dx. That's the main thing you have to remember and keep in mind. When you do this, you're actually applying the chain rule, right, whenever you take that derivative. Okay, let's try another little example here. Let's try this one here. So x plus 3y. Now, to start off, the derivative of x, taking the derivative of x with respect to x, the variables agree, the derivative of x is 1. So, to start off, you take the derivative of your first term, so it's 1. Now, the derivative of 3y. Now, the derivative of 3x is 3. So, the derivative of 3y is 3 times dy over dx. You take the derivative just like you would if this was 3x, but you've got to leave dy over dx as a factor. And once again, just like you would with an x factor, but you have to leave dy over dx as a factor. So the derivative of 3x would be 3, but the derivative of 3y is 3 times dy over dx. Now let's do one more. We'll try another simple example. This will be our last one, the last example on this video. So we're going to look at the next video. We'll do several more examples. Okay, what about the derivative of x times y squared? Now, first thing you ought to notice now, x times y squared, now that's a product. So if we're going to take the derivative of this expression here, okay, we've got to use the product rule. Now, remember the product rule, x will be your first term times the derivative of the second, so x times the derivative of y squared. So the first times the derivative of the second plus the second times the derivative of the first. So the rest of the expression will look like this. So x times the derivative of y squared plus y squared times the derivative of x. So we set this up now using the product rule. Now taking the derivative of y squared would be 2y times dy over dx, and the derivative of x is 1. So as you take your derivative, this is what it looks like. X times 2y times dy over dx. So remember, you take the derivative of y squared, just like you would x squared. The derivative of x squared would be 2x, so the derivative of y squared would be 2y times dy over dx. You've got that extra factor in this term here. Then plus, then y squared times the derivative of x is just y squared times 1. So our derivative looks like this right here. So x times 2y would be 2xy, so we just kind of rearrange that times dy over dx plus y squared. So this will be the last example we're going to do on this particular video. On my next video, we're going to pull up our smart board and we're going to do a bunch more examples. Right? But that's it for this. Hopefully this little introduction will kind of give you some idea or idea how we're taking the derivative of an equation without solving the equation for y. Right? So these terms here, we can take the derivative very quickly the way they sit without actually solving for y. So a couple guidelines now we want to mention. Now this, we want to make sure you understand these. There's a couple steps you go through as you take the derivative using implicit differentiation. So first, number one, we're going to differentiate all the terms with respect to x. All right, so differentiate all terms with respect to x. Remember now, when you take the derivative of a y factor with respect to x, you've got to leave dy over dx as a factor. So that's the first thing you do. Take the derivative the way it is. Okay, you don't have to rearrange it or anything like this. Take the derivative the way it is. Next. Okay, you want to get, now it's possible that some of these equations or some of these equations you'll be looking at, they may have several dy dx terms in them. So you may have several y factors and you may have more than one dy over dx factor. Now if that's the case, you want to get all the terms with dy dx on the left-hand side of your equal sign and then all the other terms on the right. So that's important there. So you want any of the factors have dy dx, you want them on the left, move everything else to the right. And then the third step, you got to factor dy dx out. Right, so if you have more than one dy dx factor, we're trying to solve for dy over dx. So to get dy dx by itself, we have to factor dy dx out. Now you'll see this in some of our examples on our next video. The last thing you want to do is solve for dy over dx. So when you get dy over dx equals your expression, you have your derivative. You remember that the derivative is slope, so we can also use that expression to find the slope of our tangent line at a particular point on a curve. So once again, let me summarize. The guidelines for implicit differentiation: number one, differentiate all the terms with respect to x. Number two, you're going to get all the terms that have dy dx on the left, everything else on the right. Number three, if you have two or more dy dx factors, you have to factor dy dx out. And then last, you're going to solve for dy over dx. So that'll kind of summarize our 4 steps. And then if you follow these steps, you can pretty well differentiate about, use implicit differentiation to find about any equation. So that finishes our video, and the second video will start here in just a minute.